In this unit, we will take the first steps with VESTA.
If you haven't downloaded it already, follow this link, which is also given right next to the video.
Click on Download. Now choose your operating system. In my case, this is the 64-bit version of Windows. And download the installation files. You'll receive a zip file. And I just extract this to some folder on my hard drive. On my computer I chose the C directory. And here I now have a folder called VESTA. And in this folder you'll find an application called VESTA. There's no further installation needed. You just double click it and you run VESTA. Now let's build the crystal structure of chalcanthite. We have gathered all the necessary input in a PDF. Open it and you will find the chemical formula, the dimensions of the unit cell, and the atomic parameters. Please note that we excluded all hydrogen atoms to keep this example simple. Now let's transfer this data to VESTA. I will place the windows of the PDF and VESTA side by side so everything is nice and in order. Now let's transfer this data into VESTA. Click File, New Structure, and give this phase a more descriptive name. Now there are many parameters to manipulate, but for now we'll concentrate on just a few. And they are located in the Structure Parameters tab and in the Unit Cell tab. To save your input, just click OK. Now we have created a new phase called chalcanthite. VESTA automatically creates a unit cell that is some sort of cubicle, but that is not what we need. To change the parameters of the unit cell, click Edit, Edit Data, Unit Cell. And you can see in the options that the crystal system is already set to triclinic, but we need to change the space group. As you can see in our PDF, the space group is P1 bar, which can also be written in this manner. Space group P1 bar has an inversion center. Those symmetry operations, like inversion or mirroring, are very important to space groups, and we will explain those later on. But for now, just check this little box here to P1 bar. Now let's enter the unit cell parameters. The value for A is 5.9553. So we enter 5.9553. Let's fill in the values for B and C. Of course, you can also copy and paste the values to save some time. Let's also change the angles of the unit cell. Fill in the values for alpha, beta, and gamma. And click OK. Now you see that the unit cell no longer has 90 degrees angles and is somewhat skew. Now all the parameters of the unit cell are correct, but it is still empty. Let's add an atom. Go to Edit, Edit Data, Structure Parameters. Click New to add a new atom. And hit Symbol to choose copper from the periodic table. And we label this with copper 1. Now in the PDF, the atomic parameters of copper 1 are given as a half and a half and a half. So we enter the coordinates as 0.5, 0.5, 0.5. We hit OK to save. And now there's a copper atom right in the center of the unit cell. Let's add some more atoms. Click Edit, Edit Data, Structure Parameters. Click New for another atom and choose copper again. This time label it copper 2. Now the coordinates for copper 2 are given as a half, 0 and 0. So here we write 0.5 and leave the other two as 0. Now let's add sulfur. Choose sulfur and label it sulfur 1. The coordinates are a bit more complicated here. Make sure you enter the negative value correctly. Click OK. Now sulfur is in here as well. So, you have added copper and sulfur to the unit cell. But the oxygen atoms are still missing. When you enter those 9 missing oxygen atoms, you'll end up with a structure that looks like this. Now that we have entered all the atoms, we no longer need the PDF. So go full screen with VESTA. Now we can play around with the structure a little bit. Look at it from different angles, for example along the B axis or along the C axis. Let's add some bonds. Go to Edit, Bonds, and now we want to search for bonds. We create a new type of bond, and we want to search for atoms that are bonded to copper. The minimum bond length is set to 0, and the maximum bond length is set to 1.6. Let's see what happens. Nothing. So let's extend the bonding range a little bit. Go to Edit, Bonds. Let's try, for example, 3 angstroms. Click OK. And now you can see that each copper atom is surrounded by 6 oxygen atoms in an octahedral arrangement. Let's do the same again for sulfur. And we again search for atoms that are bonded to sulfur within a radius of 3 angstroms. And now we can see that sulfur is surrounded by 4 oxygen atoms in a tetrahedral arrangement. Maybe you not only want to display one unit cell. Let's extend the range. Go to Objects, Boundary, and extend the range a little bit. Let it go from 0 to 2 in all 3 directions. We hit OK. And now we get 2 by 2 by 2 unit cells. And this is already a very small crystal, as it has a repeating arrangement of atoms. Okay. I suggest that you play around with the settings a little bit. Try some different representations, such as the space filling or the polyhedral style.